How y'all doing today? Also, happy Friday, by the way. Any questions or etc. before we get started today? Yes.
So on our quizzes on the homework, it doesn't give us a grade afterwards?
That's not what
Or
it's supposed to do.
Did anyone else do it? Okay. Yeah, it's like you just do it, and then once you get the problems right, or I guess wrong, then it kind of just leaves it blank. It doesn't give you like a score afterwards. Which doesn't have to be a problem for right now, but I wanted to make sure that it wasn't on my end.
Right. That might mean that some of the quizzes, some of the assignments, possibly plural settings are like not correct. So that means I need to mess around with, and to look at each one's individual settings. Thank you for letting me know.
Yeah, I think at least the homework was like normal, but the quiz 1/2, where it's like 3 questions or something, was weird.
Okay.
But otherwise, I don't know.
Writing a quick note to myself. Thank you for telling me.
Yep.
Anything else on your minds before we get started? Okay. Well, we've been talking about chapter 4 for about a week, actually about 2 weeks now, and I feel like we've got a pretty good foundation for Newton's laws and different types of force. And so my goal now is to move on to chapter 5, where we look at look at the next application of force, namely how we use energy in order to use force and do work. I've got a calendar up just to point out my plan for the next couple of weeks. We're starting chapter 5 today on Friday the 22nd. I usually plan for a chapter to take about a week, which is to say about 3 lectures, which means we'll be wrapping up chapter 5 around Wednesday the 27th, which gives us Friday the 29th to start reviewing for the upcoming test. Said test, again, will be on chapters 1 through 5, and it will take place the week of October 2nd through 6th during lab time. So whenever a test happens or exam, I do it for both tests and also the exam. Whenever a test or exam happens in here, I always want to take time before it is done to show you guys everything that's going to be on it, go over all the material from the chapters, and I always make a practice test that students can do. I also put up an answer key for that practice test. And I write the practice test myself after the test is finalized to make sure that it is on the same types of things. So if I posted to Brightspace, if you can do the practice test, you should be fine on the test. And my goal is be wrapping up chapter 5 on the 27th, 29th. We will spend summarizing the past 2 months, I guess. 1 month and a half. Summarizing everything so that we all feel comfortable before the test. And then this week, 2nd through 6th, you will show up to lab time and take the test there. So the test will not be during class, it'll be during lab time. There is no normal lab this week. You show up and take the test instead. And that means we also still have lecture this week for review and studying. During that week, I invite students to ask me questions from the practice test, ask me questions from the homework, because there is technically 5 chapters worth of homework and quiz that is also good study practice. And I do recommend students be working on those, because right after the test week, we actually have 2 days off, yay, and then midterm scores go out Friday the 13th. That still feels ominous to say out loud. And the midterm score for this class is going to be your current class average, which is test, lab, homework, and quiz. So if you do the homeworks and quizzes, that is not only practice for the test, it also directly helps your midterm score. So I do recommend that you work on those. If you don't work on them yet, if you don't complete them yet, it's not the end of the world, because like they aren't due until the end of the course. The midterm score is just a check-in. It's not like you have to be passing by the midterm or anything. But I still recommend doing it, because if nothing else, it's good studying, and it helps your midterm score, so that the midterm actual letter grade is nicer. How you guys feel? All right. I think that's all the beginning of class announcements. Now, for Chapter 5 itself, this is going to be a direct continuation from what we've been talking about the past couple of weeks, because in order to, the main premise of Chapter 5 is going to be work, the physics concept of work. And in order to do work, you need force. So we've been building our understanding of force, and now we are looking at the various applications of force. So, work is one of those words that has a few different meanings. The physics definition of work is the use and transfer of energy, alternatively, the transformation of energy. Work can be thought of as all three of these things, technically. And that is because anytime you have ever exerted force in your life, either on an object or even just moving your own body around, because there are loads of internal forces within you, that has involved using force to do work. Broadly speaking, we use forces to do work. And that work is, again, we think of work as accomplishing a task, usually. And when you, again, physics definition, accomplish a task, you are using force to use up energy to get that task accomplished. This is why exerting force tires you out. If you exert force for too long, you eventually run out of energy and need a break, right? If you push anything too long, even just moving your own body around too much, you run out of energy and have to stop. And that is because force does work, work takes energy. So the concept of energy is still kind of tied up into the concept of force. And one of the ways that we calculate work in this class is with this formula. Actually, I'm going to roll the board up and point out that P is supposed to be a parallel symbol, and PowerPoint is messing up on me. This is a new formula, and work is a new variable, so I want to take a sec to define it. Formula says that work is equal to force parallel times displacement. Work is a new variable. Again, it is the measurement of how much energy you are using and successfully transferring when you undergo some sort of a task. Whenever you do anything, you use up energy, and that includes even just moving your own arm around. And so the amount of energy that you use up doing pretty much any action is at minimum equal to the force required to undertake that action times the net displacement of the object you are exerting that force upon. You push on something, it moves, you have done work and used up energy in the task. Okay so far? All right, work is a new variable, so a couple quick things about it. It is not a vector. I want to point that out. Work is not a vector, which is good. It doesn't have a direction. These two things have a direction, but because of, in the majors class, we differentiate between different types of vector multiplication. We don't really do that so much here, but to briefly elaborate, these two vectors are multiplied together in such a way that their directions cancel out. And as a result, work just isn't a vector. So, not a vector. Work itself has no direction, even though the force and the displacement do have directions. And since work is a measurement of how much energy a task uses up, it shares a unit with energy. The metric unit for energy that we're going to be using in this class is joules, spelled like the French name, not like diamonds. So joules, abbreviated to J, is the metric unit for work. And depending on which floor of this or the adjacent building you like to hang out on, you may be more familiar with calories as the unit for energy. Why can't I talk today? They measure the same thing, it's just different units. The ratio is 1 joule to about 1/4 of a calorie. Likewise, 1 calorie is about 4 joules. I can never remember which one is defined as the amount of heat needed to increase 1 gram of water by 1 degree Celsius. Calories. Calories are defined as 1 calorie is the energy needed to increase 1 gram of water by 1 degree Celsius, which is probably why it's the preferred unit for casts. But we're going to use joules. And that's specifically because for our formula here, 1 joule is the amount of energy required to exert a 1 Newton force times a 1 meter displacement. So that's why we like joules. That is the definition of joules. It reflects back to newtons, so that's why we're using it here. Questions so far? Also point out briefly on your formula sheet, this formula is in the top part of the energy stuff bracket, and here it does use the parallel symbol. So put the parallel symbol in your notes. We'll explain why that's there briefly, shortly. And again, this means that anytime you exert a force on something and it moves, you are doing work and you are using up your body's own energy and giving it to whatever it is you are acting on. And this basically means every single action you take consumes some amount of energy, not just using it up, but also transforming it into other forms and transferring it to different objects. Now, the definition of work mentions energy, and I need to define energy real quick, how we are going to describe it in this class. And the problem with energy is it is weird and kind of hard to describe from a physicist's perspective. The weirdest thing about energy is you cannot detect it directly. You can only detect it indirectly. Examples currently shown on screen are places where people might think they can see energy. Lightning is easily the most classical historical example. Early humans saw lightning and were probably terrified. And there is energy involved in lightning, but what you're seeing isn't the energy. Likewise, I grew up on a lot of 90s cartoons. And no matter how powerful the character of your favorite anime is, no matter how brightly they are glowing, the glowing is not an energy level. It is energy they are giving off, but you're not seeing the energy directly, you're seeing light given off by the thing that has energy. You do not see energy directly, you just see what matter does when it has energy. And glowing is one of the things that matter does when it has energy. In the case of lightning, the light happens because as energy travels, as electrical energy travels through the air flash heats into plasma, and the plasma glows. Same thing technically happening in the light bulbs right now. I assume the same thing here, however much science goes into this process. So again, The best definition that physics can provide for energy is it is something that matter can possess that allows it to do stuff. And we always end up measuring it indirectly. Off the top of your heads, what are some common forms of energy or some common phenomenon where you think you can detect energy using your human senses? Heat. I'm going to write that down as thermal. What else?
Like sound.
Sound.
Or like when it's really loud and you can like feel the energy.
That is true. The process of sound. Sound is a mechanical wave that does translate, that does take energy from one place and send it through the air to another place. So technically when you hear me speaking, I am literally just screaming energy into your eardrums. I am going to list that as kinetic energy, since it involves the motion of the air. Yes? Electrical, very good. Again, lightning is not directly energy, you just see it because matter is glowing. Other forms of energy, other places where you can detect energy. Yes. Radiation is given off by things that possess energy. I am just going to summarize that by saying light, because gamma and light are different flavors of the same thing. All right, this is a good list. These are all different forms of energy that you are possibly familiar with. I know, again, depending on what floor of the science buildings you hang out on, you're probably very used to talking about thermal energy. They're all different forms, and you can detect them indirectly, but not ever directly. Again, in relation to human senses. We will address most of, well, we're actually not going to talk about electrical that much this semester. If you take 1510, that's when we do electricity. And I do talk a little bit about waves at the end of the class. I'll talk about how light works a bit. We're going to focus mostly on sound at that point, though. But these are all good forms of energy, and again, you only detect them indirectly, right? You can't look at something and know how much thermal energy it has. You can tell if it's hot, if it's glowing, maybe, but you can't look at it and know inherently, 300 joules of thermal energy. You don't see the energy, you just see if it's giving off light. And again, the light is not the heat itself. And you only really know it's there for sure when you touch it and burn yourself. And again, that's not directly detecting energy, that's just detecting pain from your nerves being scrambled from the thermal energy. You can't even really tell when it's there, you only tell if it's leaving you or entering you. Because your nerves are not a thermostat, your nerves just detect the flow of heat. Because right now in this room, do you feel hot or cold, or do you just feel nothing in relation to temperature? That might be up to individual interpretation, but right now, I feel nothing in relationship to temperature. And that's because right now, my body's in thermal homeostasis. Energy is not really leaving me or entering me, because that's all you can detect with your nerve endings. I have heat. I know this because I'm not at absolute zero, but I can't feel it because that's not what my nerves are designed for. I can only feel when heat enters me as the perception of hot, and when heat exits me as the perception of cold. And you can't really tell how much, well, you kind of can. Too much heat feels too hot, and too much heat leaving feels too cold. But that's just heat flow. That's not like the amount of joules in your body or the amount of joules of the thing you're touching. So again, indirectly through very specific nerve interactions. Likewise, you can only tell something has kinetic energy if you can see it moving, right? And even then, that's not a great metric because everything is moving. Right now, we're hurtling through space at Mach 9, right? Because the planet we're on is moving through space. But we can't detect that kinetic energy because we have the same reference point as the planet we're on. So from our perspectives, nothing in this room is moving that much. But from like a stationary galactic perspective, we have a lot of kinetic energy. So that one's hard to track because it's entirely relative. Electrical energy, again, that's technically something that happens when electrons possess energy. So the electricity itself is not energy, it's matter that's moving really fast in a straight line. And electricity is made of matter, weird to think about, but electrons are matter. And that means technically you could weigh a lightning bolt if you don't burn yourself, and you could like hold it in place long enough, because the lightning bolt is made of electrons and air. So this is a specific form of matter that has energy and is usually moving all together in one direction. So again, not energy itself, matter that possesses energy. Light is probably the closest way we have to detect energy itself, and even then it's still not great, because light is, when something radiates light, it uses energy to create the photon, and the photon itself is technically an electric field and a magnetic field traveling together at the same time, and fields aren't directly energy. So light's kind of a weird fuzzy space, as is every form of radiation. It's technically not energy itself, but it's probably the closest thing. It's the closest thing to energy that we can normally, traditionally detect directly. And even then, it's still not perfect. All that to say, I've been monologuing for a while because I find this topic interesting. The best definition of energy physics can provide is it is this invisible thing that matter can possess that lets it do stuff. And the best way we have to detect energy is when matter is using it to do stuff, and we detect the stuff that the matter is doing. To reference that back to heat real quick, we can only really tell something has heat if its particles are jumping around because they have it. And if it doesn't have heat, that particle is just stationary. And then you have absolute zero, which never really happens. Again, I'm just rambling at this point. Questions for right now? All right, so this is the definition of energy we're going to work from. To talk back to the definition of work real quick, work can be thought of not only as using energy and giving it to something, but also transforming energy. Because everything over there references a different form of energy, and all those different forms can convert back and forth into each other. The act of doing work often takes one form of energy and transforms it into another. In particular, just moving your own body around, because biologists, please correct me if I misspeak. When you move, your muscles take stored chemical potential energy and then turn it into mechanical kinetic energy in order to move, right? ATP is a form of stored chemical potential, right? Muscles undergo a process that takes that stored chemical potential, turns it into mechanical kinetic, and then you can transfer that mechanical kinetic into another object or just use it yourself. So again, every time you move, there is an energy transformation going on. So, to tap back real quick. Work. The use, transfer, or transformation of energy. And now we're going to look at different scenarios where any combination of these three things occurs. So, tiny bit of sample math for that new formula. We're going to do some work. Fun fact, since the definition of work is just using energy, exerting force, and moving something one distance, if a parent or guardian asks you if you've done your work yet today, if you do this, you can honestly answer yes. In this case, the work we're going to be doing is pushing a large box around. I've been making a lot of those examples lately. We're going to apply a 50 Newton force to that box, and that box is, as a result, going to displace 10 meters in the same direction forward as the force we're exerting. So, first thing, how much work do we accomplish in this scenario? $500 joules. It's not a trick. Work equals force parallel times displacement. So 50 times 10 is 500 joules, which would be using up like 125 heat calories, or 0.1 food calories. Sorry, am I in the way? So that would be the work that you accomplish in this task. And that means that your body took, at minimum, 500 joules of your own stored chemical potential, transformed it into mechanical kinetic, and then gave that mechanical kinetic energy to the box. So once again, transformation, turning it from chemical potential into mechanical kinetic, using it to move yourself in the box, and as a result, transferring the energy into the box to allow it to move. Feel good? Thus far, at least? Okay. Now, get to the weird stuff. Any force is capable of doing work. Any force, regardless of where it comes from. We often think of I've been using examples primarily of the force that you exert, because there is a lot of using, transferring, and transforming in that scenario, in that example. But any force can do work. And there are currently, bless you, loads of forces acting on this box if we're dragging it across the ground, right? As we've been talking about all week. So, as an example, bless you, force of gravity on the box. If the box weighs 100 newtons, is gravity going to do work on this box as it moves? Very good. Gravity is capable of doing work because any force can do work, but the requisite for doing work is that the object has to move parallel to the force that you are applying. What axis does this box move in right now? And gravity points in the Y. So gravity can do work, it's just not accomplishing anything in this scenario. This is what gravity doing work looks like, because it falls parallel to the force. But in this case, the motion is perpendicular to the force, and so gravity is not accomplishing anything in this scenario. And I will demonstrate that mathematically. I'm going to show two different work gravity calculations, so that's just why it's WG. For this formula to work, there's the requisite that the force be parallel to the displacement. And that's why this symbol is always going to live here when I write this formula. Force and displacement need to be parallel to each other. And there's two ways that we can look at this picture to prove that gravity's not doing work here. One, let's start by writing out the force of gravity, the full 100 newtons. Gravity points in the y-axis, so what is this box's y displacement? 0. There is no parallel vertical displacement going on here. All the displacement is in the x-axis. Therefore, if we plug in the magnitude of parallel displacement to the y-axis, that is 0. So gravity is accomplishing 0 joules worth of work right now. Likewise, we could look at it from the other perspective, which is to say, we start with the x displacement, and then we ask ourselves, what is the x-axis force that gravity is exerting on this box that would be parallel to that displacement? It's 0 again, because gravity's pulling entirely in the y. It has no x component. And that is another way that where gravity is 0 in this case. So either axis perspective, gravity does no work in this case. The motion must be parallel to the displacement for this formula to successfully give you an amount of work that force is accomplishing. To give another example, let's say that let's say that I'm an extra in a Marvel movie, and I'm trying to move something heavy in a scene where the Hulk is present. I'm going to try to push the box up, and the Hulk is going to push the box to the right. As a result, the box moves to the right. The Hulk will accomplish something, big x-axis force times big x-axis displacement. Do I accomplish anything other than looking silly? No, I really use up my own energy here. The one flaw with this formula is, if I'm pushing pointlessly against something, like say against this wall that will never move when I push it, I do use up my own energy, I'm just not accomplishing anything with it. I'm not really giving any mechanical energy to the wall as a result of this. I'm just pointlessly tiring myself out. So, the formula is not an absolute metric for the amount of energy that I burn. It's just a metric for how much energy the object gains as a result. Because the object is the thing that's moving. The displacement is the object's perspective. So, this formula works to tell you how much energy something gains, not necessarily how much energy had to be used up in the process. You can use force, accomplish no work, and still have an energy deficit if you're, again, kind of pushing pointlessly. Because even if you don't displace something, you still use up the energy when you use your muscles to exert force. I think I just summarized what this said. The formula also really only tells you the minimum amount of work needed, the minimum amount of energy that the, say, box would need in this case to make this work. And that is because of largely friction. Most mechanical processes have some sort of an efficiency dictated by the internal friction of the machine. And what these calculations would indicate is that the box needs at least 500 joules worth of mechanical energy in order to accomplish that task. And an inefficient human body is going to burn more than 500 joules worth of energy doing this because of mechanical inefficiency and non-conserved work. I mentioned that any force can do work. Any force is able to transform energy. And within physics, we tend to categorize work on whether or not it is conserved or not. Conserved work, indicated by getting a positive answer from this formula, means that the energy you use up is in a usable mechanical form after the fact. If I use my own energy to chuck a baseball really fast, mechanical energy transfers out of my arm into the baseball, and the baseball rockets off with mechanical kinetic energy that we can observe as a result. That is a conserved process, conserved work, because we can still account for all the energy in a mechanical state. However much energy my arm gives up, the baseball would have the same amount of kinetic energy, at least immediately after I throw it. All in a mechanical form, all of which can be used again. If that baseball strikes something, it will then still transfer all of that mechanical kinetic energy into whatever it hits, possibly some form of generator to take that energy and turn it back into a usable form. This is contrasted to non-conserved work, which you usually get when this formula spits out a negative answer, which really only happens with friction, as I will demonstrate shortly. Non-conserved work means that whatever force is responsible for it is taking energy away from something and likely turning it into a state where it can't be used again. There's only so much energy in the universe. We like to store it and save it as much as possible. But I mentioned earlier in the week that friction is just a constant pest. One of the reasons friction is a constant pest is because it is the universe's single greatest source of non-conserved negative work that takes energy away from things and renders it largely useless. Let us elaborate mathematically. This is the same box question, I've just added an extra part to it. As we push it forwards, friction is going to exert a force of 30 newtons backwards upon it. So to add one more force to this drawing, friction opposes motion, so if the box is moving forward, friction will automatically point in the reverse direction. So here I'll write negative 30 to the left. And once again, any force can do work, as long as the force itself is parallel to the displacement. And even though it's in the opposite direction, this friction is still parallel to the displacement. It's within the same axis, meaning that this formula didn't give us a number for gravity, but it can for friction because it meets the parallel rule. So work friction would be negative 30 times positive 10. They have to be in the same axis, and you do still have to consider if they're pointing in the same direction or not. If they are not pointing in the same direction, displacement and the force, one of them is going to be negative, and that's when you get a negative answer for work, when the force opposes the motion. Again, friction is the main thing that does that. And that here would give us negative work, non-conserved work, because what friction is doing here is it is trying to rob this box of its energy and stop it from moving. This is the biggest universal crime that friction commits. It takes energy away. It means that we can't be using it actively. Like, if we want this box to go as fast as possible, we want to get the task done and over with, we're going to give it a lot of energy to try to get it there quickly, and friction is just taking more and more of it away every single time. Every single motion, every single action that you will ever take, friction is there, ruining the mechanical efficiency and sucking energy out of your muscles, making your life harder. So friction takes the energy away. As we will discuss more and more as next week goes on, even when friction takes energy away, that energy still exists. There's this thing called the conservation of energy that states energy can't be destroyed. It has to go somewhere. So in this case, if friction takes 300 joules of energy away, where does it go? It's not just annihilated, it has to go somewhere. Yep, into the surface that exerted the friction in the form of heat. You ever noticed how when a car slams on the brakes and comes to a stop, the skid marks it leaves are hot? That's because literally friction took all of the car's kinetic energy and just turned it into heat in the asphalt. Friction takes energy away and turns it into heat. And heat is useful in the winter, but in pretty much any other context, it's a big old pain. Because once friction turns something into heat, we can't really usually get it back. And so all of that gas you burned to make the car go fast, all the energy you generated is now just gone. It's just making the earth warmer, which is kind of a problem for several reasons at the moment, if we're being honest. Friction, again, definition of work is the use, transfer, and transformation of energy. When friction does work, it takes the energy away and turns it into heat. And once it's heat, we can't really do anything about that. We don't really have a machine that can harvest thermal energy out of the earth and turn it back into like electrical or mechanical or something. And this is one of the things that contributes to that term scientists throw around, heat death of the universe. When all energy is heat and we can't use it to do anything anymore, and we all just sit in a boiling nebula. I'm monologuing a lot because I find these concepts interesting. How are you guys taking this information? Questions thus far? Okay. So to summarize, when you do work and give something energy, friction then takes that energy away. I gave the eraser kinetic, and then friction just turned it into heat in my desk, and as a result, the eraser now stops. This is also summarily why you overheat if you do too much physical activity, because there's friction in your muscles. Again, not a biologist, so please correct me if I'm not totally right, but your muscle fibers have to slide across each other to do their job, right? And likewise, they're sliding over everything else that they are touching inside of you. And any time matter moves over matter, there's friction. So the reason you warm up when you do physical activity is internal friction taking your precious mechanical energy and just turning it into heat. So you overheat because of friction, and all your machines do too, because it turns out electricity has friction as well, as does all the moving parts in your car. So that is why machines need coolant systems, and it's why you need a coolant system. Stay hydrated. So yeah, friction's a pain, and I usually monologue about it because I want to drive that point home. I asked this like 30 seconds ago. Questions? Yes. Oh.
Oh, there is a bug behind you.
Oh, I think that's a mayfly. Yikes. I want that dead. Pardon to whoever's athletic letter this is.
Use the stick.
See the slopes.
Yo. Wow.
That's the most impressive thing I'll do all day. It is dead. Any other questions? At least once a semester, there's usually a bug incident where like a stinging insect gets in here. And usually I try to just like trap it rather than risk killing it and making it mad. But mayflies don't sting, so no mercy. All right. I think I've gotten through the main list of points I wanted to monologue about today. Sorry. Next week we're going to talk about conservation of energy, different forms of energy, transforming different forms of energy into each other, and also the use of energy over time, which is power. And then we will move into test prep territory. Questions at this time? All right. It's Friday, so you can start packing up and get to your routine quicker. I'll just point out, next two things we'll do is look at kinetic, followed by gravitational potential. So stay tuned for that. Questions? All right, have a great day. Let me know if you need anything.